All right, now let's get more into the electricity part of electrochemistry. First, we're going to talk about electrical current. We can correlate electrical current to current of liquid in a stream. So if we're looking, say, at this lovely river here, and we're talking about the current, we're talking about how much water passes by in a given period of time. Identically, for electrical current, we're talking about the amount of electrical charge that passes by a single spot in a given period of time. Now we can talk about current in a wire, or we could talk about ions flowing through a solution. It works the same way. We're looking at electrons flowing by over a period of time. Now, electricity can flow directly between atoms. So here, if you put a zinc strip into copper sulfate, the electrons will transfer from the zinc to the copper in the solution, and we'll get zinc ions, and then the copper will deposit onto the zinc strip. So you can see over time, our strip of zinc becomes coated in the copper. Or we can set up a voltaic cell here and have the electrons transfer indirectly between atoms. So here we put a zinc anode and zinc nitrate in solution, and our electrons will flow from the solid zinc through the wire and be transferred to the cathode, where the copper will gain the electron and deposit onto the cathode. So the zinc is losing an electron goes this way, the zinc goes into solution, the copper is gaining the electron, and copper from the solution is depositing onto the solid. Now some terms here. The anode in a voltaic cell is where the oxidation reaction takes place. It is negatively charged. And then, so the electrons are flowing from that kind of reservoir of negative charge this way. And then the cathode is where the reduction reaction takes place. It's positively charged, so it's attracting those electrons. And then it's important to balance the charges. So we have a salt bridge here that has potassium nitrate in it. And so as negative charge leaves here, the nitrate can go into solution and balance those charges. Similarly, as electrons build up over here, the potassium can go into solution so that we end up with a balanced overall charge. If you don't have the salt bridge, this won't work. Oh, one other thing, for me to remember, I find it helps to remember that anode starts with a vowel and oxidation starts with a vowel, cathode starts with a consonant, reduction starts with a consonant. That's something that helps me remember. You can use it or not, up to you. Okay, we have some terms on this page. Electrochemistry is the study of redox reactions that either produce or require an electric current. We're spending some time here on the ones that produce. Later on, we'll talk about the ones that require an electric current. The conversion between chemical energy and electrical energy is carried out in an electrochemical cell. A spontaneous redox reaction, one that actually produces an electrical current, takes place in a voltaic cell. Another word for a voltaic cell is a galvanic cell. A non-spontaneous redox reaction can be made to occur in an electrolytic cell by adding electrical energy, and we will talk about that towards the end of this chapter. We separate oxidation and reduction half reactions in half cells, and then electrons will flow through a wire and into a solution to make an electric current. It requires a solid electrode to allow for transfer of electrons. The example we already looked at used metal electrodes. You can also use a graphite electrode. Sometimes the reaction you're looking at won't have a solid involved, and then you'll need to use a kind of external electrode. And in order for the reaction to happen, you need ion exchange between the two half cells. You can't just build up negative charge in half of it. The electrodes, the anode, is where oxidation occurs. Anions are attracted to the electrode. It's if we're in an electrolytic cell, it's connected to the positive end of the battery. In a voltaic cell, it's the negative end, and it loses weight. A cathode is where reduction occurs. Cations are attracted to it. It's positively charged. It's connected to the negative end of a battery in an electrolytic cell, and it will gain weight in an electrolytic cell. It's where the plating takes place. Here's a voltaic cell. The salt bridge is required to complete the circuit. I mentioned that already. This is the same picture we looked at, and I already explained most of it. Current is the number of electrons that flow through the system per second. So remember our stream analogy. The unit on current is ampere or amps, and 1 amp of current is 1 coulomb of charge flowing by each second. And 1 coulomb of charge is 1.6242 times 10 to the 18th electrons per second. So a coulomb is this number right there. And then the surface area on your electrode is going to limit how many electrons can flow. So the larger battery you have, the larger surface area, the higher your possible current. Voltage is the difference in potential energy between the reactants and products. So it's a measure of energy. The unit is volt, and a volt is 1 joule of energy per coulomb of charge. So you need voltage to drive electrons through the external circuit. It's looking at that difference in potential energy. And then the amount of force pushing the electrons is the electromotive force, or EMF. So that difference in potential energy, the voltage, is the cell potential, and is going to depend on what your oxidizing agent is and what your reducing agent is. The way we measure it is called the standard EMF, or the E naught of the cell, the standard potential. Now, the standard potential, notice the naught sign there, means that it's under standard conditions, so 25 degrees Celsius, 1 atmosphere for gases, 1 molar concentration. And for your cell, it's going to be the sum of the cell potentials for the half reactions. When we're looking at voltaic cells, there is a shorthand that we sometimes use. And the way it goes is the oxidation happens first. The oxidation's on the left. So you have your electrode, then the electrolyte for the half cell on the left, the oxidation one, then a double line to indicate the salt bridge, then the electrolyte, and then the electrode for the reduction. Now the single line that you notice between the electrode and the electrolyte is a phase barrier. So this would be solid to aqueous, AQ, and then aqueous back to solid. And then if there are multiple electrolytes in the same phase, we use a comma instead of the straight line because they're in the same phase. And if that happens, we often use an inert electrode, like I mentioned earlier, that isn't participating in the reaction per se, but is capable of transferring electrons. And then the double line in the middle is the salt bridge. So if we look here, we can write our shorthand for our voltaic cell here. We have the solid zinc on our anode, or our oxidation is oxidized to zinc 2. Then there's the salt bridge. Then our copper 2 in the aqueous phase is reduced to solid copper. So it's reactants, products is another way to look at it. I've mentioned those inert electrodes. Some redox reactions will involve changing an ion to a different oxidation state or gases. Then we will use an inert electrode. So let's look at an example here. The reduction reaction involves the manganese changing oxidation state from +7 to +2. So we have permanganate going to the manganese 2+ ion. But that doesn't involve a solid. And so we can use a platinum electrode as an inert electrode because it doesn't really react and it conducts electricity well.